be Deborah Griffin from Environment and Climate Change Canada on comparisons of CO emissions globally. So Deborah, I see you there. Could you?
Yep. Thank you. Sorry, I'm just gonna share my screen. Okay, can you see that okay?
Yep, looks good. Go ahead, please.
Okay, wonderful. I have that little sharing thing in the bottom, but I think that's okay. All right, perfect. So I'll be talking about a comparison of global CO. Some of the things are actually quite similar to the previous presentation, but I'll provide a little bit more of a satellite perspective, and I'm going to talk a little bit more about satellite-derived emissions. Sorry. Whoops. Sorry. Here we go. So first of all, the satellite that I'll mostly be using is TROP-OMI. I'm sure many of you have heard about that before. It was launched, just a quick reminder, it was launched in October 2017 and has a global daily coverage with a local overpass time of about 1:30 in the afternoon. And species it measures includes NO2, formaldehyde, and so on. But my focus for today will be mostly the CO product. So satellite instruments can observe the composition of the atmosphere and can provide an alternative source for deriving wildfire emissions using a direct estimate. So for example, from the TROP-OMI instrument. However, this is limited by the species that are observed. So right now I'm doing this for NO2 and CO. And also is limited by the observation and the overpasses. So currently there's once or twice a day, but future instruments will allow more frequent sampling and also better detection. And so to estimate these satellite emissions, I'll talk a little bit more about that in a few slides down the line. But basically, we need to pair them with winds to obtain an emission rate. For that, I'm using the ERA5 winds. And the emissions can be derived either by fitting a plume function or by calculating a flux across the plume. And again, I'll be talking about this in a little bit. So just to present how fires from TROP-OMI view look like. Here, first of all, this was a little fire, horsefly fire in Montana in 2019. Here's what it looks like with the VS True color image. You can see the thermal anomalies here, and there's this little plume. So this is how it looks like from TROP-OMI CO. You can see a good enhancement where the plume is. And then further on, this is the NO2 product. Again, you can see the plume appearing right here, but what you can also see in comparison to CO, it's very noticeable that NO2 drops off rapidly. That's because of the much shorter lifetime of NO2 of maybe a couple of hours. So the NO2 enhancement stays pretty close to the fire, and you can see it a little bit further on, but much reduced. There's also the aerosol index. So this is actually a really nice product to find fire plumes or to identify the fire plume. So you can see the shape quite well here. There's also the aerosol mid-layer height product. Again, only where we actually have a plume can you see that does it even give you results. And for this specific plume, the height is roughly 2.5 kilometers. So this part is actually, going back, the aerosol mid-layer height is actually what I'm using to find the appropriate altitude for the winds to use for my emission estimate. And then there's a TROP-OMI formaldehyde. So for this fire that's relatively small, you can somewhat see a bit of an enhancement, but you can also see that the formaldehyde is quite noisy. But there are other fires for where you can see a very definite clear enhancement from the fire. So this year was another fire example. That is a fire from June 25th, and the fire was here. The winds went that way, and you can see a very clear formaldehyde enhancement. Okay, here's a quick summary of some of our recent work. So we've done emission estimates from the TRIPOMI CO product, from the TRIPOMI NO2 product, as well as the CRIS ammonia. And so here are just some figures from recent papers where we compared, so these three, we compared the satellite-derived emissions to aircraft emissions. Just talking a little bit about the figure from Kathy Hayden's paper. So here in orange is CFABS, which is the Canadian Forest Fire Emission Prediction System. That's what we use for our air quality forecasts. So these here are the orange dots. These are hourly emissions. And the first plot is PM, then CO, NOx, and NH3. The aircraft observation and emission rates are shown as this little red triangle, and it seems to agree pretty well, actually. And then in black are the satellite-derived emissions. And then the little gray dots are the FRP from GOSAR. And so one of the things that I wanted to highlight with this is that, especially when it comes to fires, the time is extremely important. So when we first looked at the aircraft versus the satellite, we were like, oh my God, this is extremely different. But that's to be expected. So because the time of the observations was only a couple of hours apart, but it's a very different time for the fire stage, actually. And so during fire XAQ, we used those aircraft measurements and compared it with the TRIPOMI derived emissions. And again, here, this is for NOx, that showed pretty good agreement. And then here is a figure showing the CO. And some that I will also address today is I used these individual fires and combined them with the FRP to get an annual budget. Okay, so the way that I derive the CO emissions, first off, I start with a simple satellite overpass. So this is here. I rotate it according to the wind direction and obtain essentially figure B. And then I fit little Gaussians across the plume to determine the plume width and to determine whether the plume is actually centered or the wind direction wasn't quite right and we need to adjust this to center this a little bit more. So based on that plume width, I then determine the size of the box and sum the mass in each of these boxes to obtain an emission rate. So this is the emission rate plotted over the distance away from the center of the fire. But you can also imagine it as rather than distance from the fire, it's actually time since emissions. So you can put that in a time perspective. This is what's shown in that last figure. It's essentially the same, but now we have it time prior to the overpass. How far has that plume traveled? So there is some evidence that maybe for the CO, we can actually, from that simple one overpass, we can actually get some sort of diurnal variability, at least within roughly 3 hours of the overpass. But this is a little bit more future work. So basically, the advantage of using this approach is that we do get global coverage and we can estimate emissions from many fires. So I get a success rate of roughly 5,000 fires per year globally. And the process is now pretty automated. And to start with, I use MODIS thermal anomalies. I cluster these, and then I attempt to estimate the emissions. And many of these fail, but roughly 5,000 I'll remain with. And so this here is very specific. So this is specific for one fire or cluster of hotspots at a very specific time. The uncertainties are roughly 40%, and again, the time is roughly 1:30 local time. But many fires will be missed that way because we have clouds, unfavorable wind conditions, or detection limit can also interfere with this, and we have limited species. So I'm doing this for CO and NOx, but Chris ammonia could also be a good candidate to be used for. And so here, that figure I showed before, but basically we did have very good agreement between TROP-OMI, directly derived emissions compared to aircraft emission estimates. Those aircraft emissions were derived from a dial high-resolution LiDAR profiles and then scaled the total carbon and integrated it through the plume height and plume width. So we expanded on this a little bit and automated it. And here is some of this, how I applied it to compare it to our CFEPS emission prediction system, or GFEPS, which is essentially the same but global. The top row here shows a good example. So this here is GEMAC, which is our air quality model. This uses the GFEPS emissions, those go in. We have a fire here on May 21st, and these are the VCDs from our model. And here shown the TROP-OMI CO VCDs. And you can see the difference. There's very little difference. It's very good agreement, also very good agreement in terms of the emissions. And here is the VS True color image. You can see that actually all the hotspots are visible. So on the bottom, in contrast, is an example where they did not agree well. This is actually the same fire just a few days later. So TROP-OMI shows a lot more CO compared to the model. The emissions that went into the model from CFEPS are much lower compared to what we derived. And here you can see that a lot of these hotspots, so the plume is a lot larger and a lot smokier. And I think it was mentioned yesterday that as well, that there are some hotspots that are underneath this thick smoke plume that are not observed. And that's actually what goes into the CFEPS emission prediction. So that's a real limitation. And so I compared this to many more fires globally where I use the time. So I interpolate the emissions to the time of the TROP-OMI overpass, which for a good fire looks like this. But looking at everything, this for all of 2019, there are many fires that are underestimated. A lot of them agree quite well, but we have a lot of them that are actually underestimated. And now a lot of inventories do not provide individual fires at specific times. So I try to think of a way how I can scale the TROP-OMI emissions to annual emissions. And to do this, I'm using FRP. So in contrast to, for example, industry emissions, where we can assume that where we have a production rate and we can assume that the emissions at 1:30 can be roughly stay the same throughout the day, or they can easily be scaled according to the production rate. This doesn't really apply to fires. They change very much throughout the day in terms of their intensity. So a good indicator to use is then the FRP. So to start off with, I compare the troponin CO emissions to the coincident modus aqua FRP. And I estimate from this, I estimate emission coefficients, which are essentially the emissions over the FRP for different vegetations. I get a correlation coefficient depending on the vegetation between 0.5 and 0.6. I think at the best I found 0.7, which is not too bad. And for the vegetation, I'm using the GLC 2000 vegetation, and I bin the emission coefficients that I get based on the vegetation map on the 0.1 by 0.1 grid, which matches the GFAS daily FRE. And from this, I can essentially scale it up to monthly or daily CO emissions on the 0.1 by 0.1 grid. So this is how it looks like for 2019. So my total emissions using that troponin FRE approach, I get 288 megatons of CO. Here in the bottom, I just wanted to highlight how the vegetation, the GLC 2000 looks like. Essentially between vegetation 1 and 9, it's some sort of trees. And I don't want to go into too much detail with this. Then we have shrub and herbaceous. And then the 16, 17, 18 is cultivated types of vegetation. So from this, roughly 2/3 of the CO2 emissions seem to be from tree vegetation, which is not surprising looking at the different regions globally. So I guess from the talk earlier, you're familiar with these. Southern Hemisphere, Africa has the highest CO emissions. And looking monthly, it's in August, which is expected, we would have the highest emissions. So combining troponin modus FRP, I can now compare this to other existing fire emission inventories. And so overall, looking at the totals, troponin FRE seems to be a little bit low. Here are the other ones. So GFAPS again is from our is the fire prediction system that goes into our air quality forecast. And then GFAS, GFAT, and FIN version 1.5 and version 2.5. Again, you can see the big difference where FIN version 2.5 is a lot higher than the rest. So, and I also wanted to mention that the troponin FRE relies on the GFAS FRE, but there's still significant differences. Depending on the region, you can see quite strong differences, for example, in the Bona region or in the IGAC region. So the region that's affected by the largest CO emissions is the Southern Hemisphere, Africa, and Southern Hemisphere, South America. And then the least affected, that's actually where all models agree pretty well, is the Europe and Middle East region. Tanner also has pretty good agreement. Here we see pretty good agreement. And then the regions where inventories are all over the place, I think, is the IGAC region. This here as well, like we have very high emissions, and then we have much lower emissions here. So there's significant differences, just what you've seen earlier in the talk. And I applied this, the tropomi emission coefficients. I applied these to the GFAS of the last 2 decades, and here's the comparison from all these different inventories of other past 2 decades, except for GFAPs, which I only had the year 2019. So in the next few slides, I don't present GFAPs because we don't have the years yet. So overall, globally, within that time frame, I should say, it seems that the CO emissions are decreasing by about 5.1 to 8.7 megatons per year. And this is nothing new. So the trend of decreasing area burned has been reported. And then again, area burned has been reported, but then the satellite observations showed only smaller decreases, not as significant as the area burned decreased. And also MOPID CO observation showed steady decreases. Now looking at that a little bit more region specific.
Interrupt, but that's 20 minutes, so I can give you another
okay.
to wrap up.
Okay, sorry. I'll just come to my summary and conclusion slide. And if I can just mention that the point of this was not to establish a new fire inventory, but rather to find a link between the direct estimates from observations and the top-down and bottom-up inventory and try and find scope for improvement. Okay, thank you. Sorry.
No, thank you very much. So there's 10 minutes allotted for questions. I haven't seen an awful lot in the chat right now. There is one hand up from Shoba. So Shoba, would you like to ask your question, please?
Yeah, sure. Yeah, Deborah, thanks. Good work. So, so your approach is very interesting because you take the techniques that were developed for deriving power plant emissions, for example, like, these line density approaches that pioneered by Dan Goldberg and few in Europe using tropomi data and applied it to fires. Now, unlike NO2 plumes, like, coming from like stacks, the smoke plumes that come from fires are very heterogeneous. Depends on the injection height and how the plume is spreading, depending on the wind speed and the altitude at which the plume is. So how are you when you do the rotated wind analysis? How are if the plume is spreading in different directions in different layers of the atmosphere? How would you handle that? The reason why when we use tropomi CO data to evaluate our emissions is we only look for fresh small plumes because of this reason that the plume is very heterogeneous. It gets dispersed and transported in different directions at different altitudes. So how CO from tropomi being a column integrated value, how do you handle that?
Yes, so good point. So one of the limitations is exactly that. So only specific kind of plumes I get estimates. That's why the number, well, is relatively low. If we have a fire that gets too spread out or too large or kind of swirls around or the wind direction change, then it's very hard to estimate. Or oftentimes in BC, you have fires here and here and here, and then there's just so many fires all across, and it's not possible to estimate it. So there's some the examples that I showed are good ideal candidates for that sort of emission estimate, and I usually go from there. When in terms of the wind, so I use the wind altitude from the tropomi aerosol layer height product. That kind of gives me a ballpark height where to get my winds from. And then that's where I actually get the wind speed and my starting wind direction. And that's why I do the little, as I showed, I fit as a first step, I fit little Gaussians all across the rotated plume to see whether the plume is actually aligned, whether the plume aligns pretty well with the wind direction from era 5, or whether it's off to the side and I just need to adjust it. So that's what I do. I hope that answered your question.
Yes, yes. Yeah, I mean, like that's clever to use the aerosol layer height from Tropomi, but that comes with a lot of uncertainty. But looks like you have a way, yeah. So you have a way of fixing it. So that's fantastic. Thank you.
Thanks, Shobha. So just on that note, maybe slightly related, Ed Heyer in the chat is asking, he says he doesn't know much about the averaging kernel for Tropomi CO, but is that something that might affect your inverse results? And I think in answering to Shobha, having this height correct and then smearing it out with the averaging kernels probably has some effect, right?
Yes, so the averaging kernel in Tropomi is relatively uniform. It does change a bit when there's cloud or thick smoke plumes. I don't account for this, as I thought by accounting for this, I might actually end up introducing more uncertainties because clouds and smoke is not differentiated within the Tropomi algorithm. So it's really hard to account for this. I did, however, find a study where somebody compared the, can't remember who, but I can look it up. Somebody compared the Fire XAQ aircraft CO to the Tropomi CO columns, and they found pretty good agreement. I think the uncertainty was roughly, or the differences were around 10%, which is much smaller than my overall uncertainty. So I wouldn't expect to have such a significant impact from that. And just a quick note, the uncertainties, the reason why they're so high is that I account a lot of uncertainty for the winds. So where the wind direction is corrected, but the wind speed is still very uncertain because we have different wind speeds and different layers. So I account quite a bit of uncertainty in that part.
Thanks, Deborah. So I see Guido has his hand up. So Guido, if you'd like to ask your question, please.
Yeah, thanks. So yeah, just great to see how you use that beautiful data from Tropomi. Maybe following up on the discussion we just had, and maybe you already answered it, I just didn't understand it. I mean, you also show results, for example, for Africa or larger regions where you cannot assess the individual plume, I guess. But I was just wondering how do you assess the emission strength of such a large region?
Sorry, how to assess the emission strength of the region?
Right, if you cannot sort of assess an individual plume, like you explained early on, but you want to go for a large region, how do you get... I'm also asking because I saw some other WRF estimates for Africa, which are also using Tropomi, which came much higher. So I'm wondering, I mean, we always see those top-down inversions as sort of the truth, but if they vary a lot, I'm wondering, is there some methodological thing that's different? Or?
Mm-hmm. I only try to use fires where I can differentiate and see a plume, or where the plume is noticeable over the background, or even if the background CO is enhanced, but it's even more enhanced in the plume. I would only use that. So I don't consider a large region. I only do very specific fires.
Thanks.
Okay, well, there are a couple more questions in the chat from Fang Jun and Pablo. So Deborah, if you don't mind taking a look at those, and another question from Shobha. So if you don't mind taking a look at those and answering them, I think we'll stay slightly ahead of time and change over to the next presentation.